Amsterdam and CWI in Random in the Netherlands. And his talk is on simulation-based computation of the workload correlation function Lévy-driven.
Okay, thank you very much for introducing me and also very much for inviting me. It's been my pleasure to be here in Cambridge. And today I'm going to talk about something with a very long title. You see it here, simulation-based computation of the workload correlation function in the Lévy-driven queue. Well, I guess I have to start with some introduction in order for you to understand what I'm talking about. And I guess the most important issue is to understand what a Lévy-driven queue is. So a Lévy-driven queue is a special queue in which the input is not, well, like a compound Poisson process, but it's a Lévy process. I'll explain in a moment how that works. What is the object that we're gonna study? The object that we're gonna study is the correlation between the workload of the queue at time 0 and the workload at time t. And there we assume that the queuing process is already in equilibrium when we start at time 0, and we wonder what information is still present at time t. Well, of course you can kind of guess that there should be a kind of positive correlation between the workload at time 0 and the workload at time t, but in fact there is quite a bit to be proven there, and this talk is about, well, what can you say about this? But as I said, the first thing that I want to explain in more detail is what a Lévy-driven queue is. In order to explain that, I first start with the natural notion of a queue in discrete time. So how does that work? Well, suppose your queuing process starts off at some level x at time 0, and what is it that the queue does? Well, there is a recursion going on, the well-known Lindley recursion, and I wrote it down there. Qn plus 1 is something like the maximum of Qn plus some net input, can be positive, can be negative, and 0. In this way you evolve and you can compute for any next point in time what the buffer content, the workload is. Well, you can iterate, and if you do that again and again, you arrive at this formula, so you can express the Q of n completely in terms of the x of n. So x of n is kind of the input process of your queuing process. This is all in discrete time, but nothing prevents you from actually looking at continuous time. And if you do that, then you get a formula of this type, where you have that your Q of t is something like the x of t, so that is the aggregated input process, and some maximum where you also recognize the process x. So for any process x, you can talk about a queue in this way. And if you go back to the normal queues that we're used to, like the MG1, then you will see that the MG1 fulfills this description. But of course we can talk about a queue, well, for any stochastic process. So we can, for instance, talk in this way about, well, a queue fed by Brownian motion. Well, this has been known for quite some time. People have been thinking about it for quite a while, and they call it reflected Brownian motion. A lot is known about that. A special case, and to that special case we restrict ourselves here, is the case of stationary increments, meaning that the input process x is such that, well, everything that arrives between t minus s and t for a given value of s stems from the same distribution irrespective of the position where you look, so irrespective of t. Well, it's well known that there is actually a steady state distribution as long as your drift is negative, as long as you kind of well, are pushed back towards the axis. Yeah, okay, yeah, that is true. There are experts in the audience. Takis also knows quite a bit about this. The process Q of t is often referred to as the workload process, and that is exactly the object that we're gonna study today. one of the questions we had in mind when starting this research was the following. Suppose you have an input process that is very strongly correlated. What happens to the workload process? Key question is the high correlation of the workload process inherited by the queue, inherited by the workload process? An example, suppose you look at fractional Brownian motion. So then your x of t has a normal distribution with certain parameters. H is the well-known Hurst parameter. And we know that if h is between 1/2 and 1, this input process is long-range dependent in the sense that these autocorrelations vanish like t to the power 2h minus 2, which is non-summable when h is between 1/2 and 1, meaning that the input process is long-range dependent. Well, then the question is, the correlation process of the workload process, is that also long-range dependent? Well, it's quite a hard question. In fact, we don't know the answer, but this was the idea why we wanted to look at this problem. There is a conjecture. We think that, in fact, the workload correlation decays essentially in the same way as the input correlation. So the queue inherits the correlation of the input, if you wish. And that would mean that your workload process is long-range dependent if h is between 1/2 and 1. Well, we haven't been able to prove this, so this is a conjecture. If somebody knows how to start proving this, be my guest. I would be very happy to join. So it was not proven yet, and the main difficulty here is that, well, the standard machinery that you can use to analyze this kind of things cannot be applied here. So usually you go to the framework of large deviations, and that works for probabilities and not so much for correlations. At least I wouldn't know how to translate a correlation in terms of something that can be analyzed through large deviations. So if somebody knows a trick there, well, I would be very interested. But my feeling is that other techniques are to be used here.
Can I just ask, why? Could you go back a slide?
Yeah.
If you want to understand how Q0 and Qt are related, why is it that you want to look at the covariance rather than some other measurement of how much related they are?
Yeah, so that is a very good question. In fact, this is just an arbitrary choice, but we would be very happy if you could think of another choice in which you could say things. In fact, in a few slides, I will go to notions in which you can analyze things. But for this specific measure, we can't. Yeah, but you're absolutely right. Any other measure that is also kind of known to say something about the correlation between Q0 and Qt is a good candidate as well. Yeah.
I'm just thinking that large deviations does give you ways to talk about the relationship between Q0 and Qt.
Yeah. Yeah.
So why are those ways not sufficient?
Well, they are sufficient, but okay, let me give you an example of one of the measures that you can analyze, and then we can talk a bit more maybe. So one of the ideas that we had was to look at things of this type. So it's in the thesis of one of my students. What did he do? Well, he looked at the joint probability of exceeding some level, let's say P of B at time 0, and at time TB you should exceed some level Q of B. P and Q are just constants, and we let B grow large. T is also a constant. Assume the Q is in stationarity at time 0, and then you can actually, well, compute the large deviations of this one. So you can use large deviation theory there, and using that machinery you can say things about, well, basically the kind of covariance for indicator functions, things of this type. Well, of course that already says quite a bit about the correlation structure, but still it's asymptotic in B, and we prefer to have something that is, well, asymptotic in T. So there is not, well, these results are already nice, I guess, but they're slightly less tangible, I guess, than results on the correlation. But I'm fully open for other measures that are maybe analyzable and still closer to the correlation. Yeah? Any questions at this point? If not, then let's move on to the actual topic of this talk. It's not going to be about FBM, but it's going to be about queues with Lévy input. But we try to answer that very same question. What can we say about, well, the correlation structure of the workload process? So what is the idea? We have a queue fed by a Lévy process. A Lévy process is some stochastic process with independent and identically distributed increments. And we wonder what can we say about the correlation of the workload. Well, something that makes it completely different from the FBM case is that now the input process is, well, kind of independent. If you look at two disjoint intervals in time, what arrives here and there, well, is completely independent of each other. And that is fully different from the FBM case where there's actually a very strong dependence. So in this case, the question is not, does the queue inherit the correlation of the input, because there is no correlation in the input, but the question is rather, what can we say about the correlation of the workload? Yeah? So I already mentioned this, so it's good to keep in mind. Probably all of you have heard about Lévy processes, some of you will have worked with it, but let me give a few remarks about Lévy processes. So the independent and identically distributed increments is the most important feature here. So we assume that they have a negative drift, so there is stability. And well, needless to say that Lévy processes are kind of key objects in applied probability. Well, you see them all the time in finance, but also in networking. So it's one of the kind of important stochastic processes. Well, in this talk, I will focus on special cases of Lévy processes. Jumps are important there. So I assume that jumps are always just in one direction. Either they are always positive, and then we call the Lévy process spectrally positive, or they're always negative, and then the Lévy process is spectrally negative. So it's well known that under, well, the condition of spectrally one-sided jumps, you can say way more than in case of, well, two-sided jumps. Well, probably you know these special cases, but let me give them anyway. One important Lévy process is Brownian motion with drift. Actually, it's both spectrally positive and spectrally negative because there are no jumps. A second example is compound Poisson with drift. So what happens there? Non-negative jobs arrive according to some Poisson process, maybe with rate lambda. Well, the jobs are IID, and they have a Laplace transform, let's say B of alpha, and the storage system is continuously depleted at rate, let's say 1. So that is the classical MG1 queue that you have there, so it fits in the framework. A recap of what we saw before: the queue at time t could be written in terms of that input process x of t, so it's exactly the same as before. And let me remind you of the fact that we assume that the queue is already in stationarity at time 0. Well, then a few words about, well, those two cases of spectrally one-sided queues. The first one is that spectrally positive case, because then the jumps are all positive. The Laplace exponent is then denoted by this lowercase phi. Well, phi is increasing and convex if we assume that the system is stable. So if we assume that the mean of x1 is negative, well, then you can prove, well, you can easily see that this phi of alpha is on 0, infinity, positive, increasing and convex. So there is an inverse, and that is called psi. Well, for technical reasons, we assume that xt is not a subordinator, but that's not important right now. Well, a lot is known about this process, or Q's fed by this process. The most important result is, of course, the famous Pollaczek-Khinchin formula. So we know the Laplace transform of the steady state. And this Laplace transform is completely specified in terms of that Laplace exponent phi. So if you know phi, then you know this kappa, and you can compute, in principle, all moments. So here I computed the mean and the variance, and well, in the rest of the talk we will assume that the variance is finite, because otherwise we cannot even speak about a correlation. So we have to do that. Let me go back to the two special cases. Brownian motion is the first one. There your phi of alpha looks like this, and if you plug it in the Pollaczek-Khinchin formula, you will see that you get an exponential distribution, a well-known fact, and that is what you retrieve here. The other one is the compound Poisson case. You can also plug it in, and there you will get the, let's say, classical Pollaczek-Khinchin formula for the MG1. So those are well-known results. The spectrally negative case is slightly easier, I feel, because, well, there is a little bit more structure. So what happens there? Capital phi of beta is, well, again, some log moment generating function. But now this phi of beta is not a bijection, so we cannot really speak about its inverse in a, well, in an unambiguous way. So here I drew a picture of this phi of beta, and because of, well, the thing over here, we have to talk about a generalized inverse, and that is what I drew there, and that is called psi, and the definition is given there. So this point over here is called beta 0, and we will need it later on. So what can you say in this case? Is there also something known about a steady state distribution, like was the case in the spectrally positive case? Yes, it is. The most important observation that you should have is that e to the power beta 0 xt, so forget about that, so that mean sign, that expectation sign, is a martingale, and there then you can use optional sampling in order to get this result. So the first time that you cross level x is a stopping time, so you can you get this formula, and from that you immediately get that the distribution of q is purely exponential, bearing in mind that q has the same distribution as the supremum over t of x of t. So here you get that q has an exponential distribution with parameter beta 0. Okay, so now I explained what spectrally positive and spectrally negative means. I explained a little bit about, well, the steady state workload, but I want to talk about, well, the correlation process, the correlation of the workload process. So there are two topics that I want to address. The first one is about, well, the kind of structural properties of the workload process, meaning that I'm going to prove, well, almost trivial things like the correlation function is positive, decreasing, and convex. Well, that sounds very plausible, but still there is something to be proven. And the second thing I'm going to talk about in the last part of my talk is about, well, let's say efficient computation of that correlation function. And I'm going to do that by using simulation. Okay, let me first recall what a correlation function is. And the correlation function is defined in the usual way, something like this. And it's not hard to see that you can actually rewrite it like this, because, well, we started in stationarity at time 0, meaning that this variance is the same as this variance. And also, well, you have here the product of the mean at time 0 and at time t, but they're the same, so you get something like that. Well, the technique I'm going to use relies heavily on Laplace transforms. So the Laplace transform of this object is called rho. So you're going to see lots of rhos later on. Well, the first result is about the spectrally positive case. There we can actually compute this Laplace transform rho of theta. And that is what I did here. It's an ugly formula, I know, but let me only kind of explain how we got it, and that's it. So what did we do? Well, the first thing we noticed is that there is a formula for the transform of the workload after an exponential amount of time. So at that first bullet you see capital T. Capital T is exponentially distributed, and we consider the workload at that exponential epoch, and we can actually compute that in terms of the Laplace exponent phi. Bear in mind that we know the distribution of Q0 because that has that Pollaczek-Khinchin distribution. So we basically have everything in hand to compute, well, the correlation. Well, then a few standard technical steps. First, you differentiate this relation with respect to S, and you let S go to 0, and then you get the transform of this conditional mean. What we want to compute is things like this. Well, how do we do that? By conditioning on the value of Q0, because then we end up in that case, and we use the result over there, and we get something like this. It's important that, well, you have the Q here and there, and you integrate with respect to the distribution of Q0. Well, we know the transform of Q0, so we can actually compute this entire thing. And then you get the formula that I gave. Well, that formula that I gave was not so transparent, I believe, but for a number of special cases, you can actually compute things. One of the cases in which you can compute things is the case of Brownian motion. So I plugged in, well, the Laplace exponent of Brownian motion, and then you get this Laplace transform of the correlation. It looks pretty ugly with that square root, but you can explicitly invert it, and what you get in the end is a formula for the correlation, an explicit formula for the correlation in terms of the distribution function and the density of the standard normal distribution. As far as I know, this is the only case in which you can explicitly invert. Well, maybe also in the MM1 case, but it's a rather delicate thing. So what was the next step for this spectrally positive case? Well, what we did was proving that this function r of t is decreasing, convex, and positive. And that was already done like 30 years ago by Teun Ott for the MG1 case. And we were interested in, let's say, bootstrapping that result to the more general case of spectrally positive Lévy traffic. So what is the idea? Well, we rely on the machinery of completely monotone functions, and I guess you can think about them as being, let's say, transforms of positive random variables. And using that property and all kinds of properties of those completely monotone functions, you can prove many things. I'll demonstrate that for the spectrally negative case. So we did it for the spectrally positive case as well, but I chose to only do it for the spectrally negative case. Another thing that we were interested in at that time were the asymptotics of R when t grows large. I'll also say a little bit about that later on. Interesting, by the way, was that the proof of Ott was quite lengthy in terms of pages. I think it was maybe 3 or 4 pages for the MG1 case. And we looked at a more general case, namely spectrally positive, and our proof was like half a page. And that is, well, something that you see quite often, I guess, that when you go to a more appropriate framework, that your proof kind of shrinks. So that also happened here. He used all kinds of explicit things about, well, the busy period distribution and all kinds of other things. We didn't have to do that, and that saved a lot of work. Okay, but how about the spectrally negative case? In order to say something about that, well, a key notion is the so-called Q-scale function. Well, you can forget about the precise form here, but what it is that there is something like a WQ, and that's a strictly increasing and continuous function of which we know its Laplace transform, and that Laplace transform is completely specified in terms of that function capital phi. In addition, there's also the z of q, and that is expressed again in terms of this w of q. Again, the precise form is not important here. Well, we need this definition. And why do we need it? Well, because we want to use a result by Martin Pistorius a couple of years ago, and he looked at the density of qt given that q0 is x. So with a little bit of abuse of notation, this transform with respect to time. So then you're basically looking at an exponential epoch because you weigh the density at time t with e to the power minus qt. He could express that fully in terms of that z and w that I introduced. In other words, with t being again exponentially distributed with parameter q, well, you can compute this transform where you have that capital T is an exponential epoch, but you also have a transform with respect to that starting point x, so the amount that you have at time x. And remember that in this case the distribution at time 0 has an exponential distribution. So we're pretty close to starting off at equilibrium. So we have to plug in that beta 0 for beta, and then we start at equilibrium. Well, the I1 and I2 can be calculated. It takes quite a while, but in the end you arrive at these beautiful expressions. And that means that we have an expression for this beast. I didn't write it down, but you can do a few sanity checks to convince yourself that everything is sound. And the first one, of course, is plugging in alpha is 0. If you do that here, plugging in alpha is 0, then you will indeed get 1. So that is reassuring. The other thing we did was plugging in beta as beta 0. And what you then get is beta 0 over beta 0 plus alpha. And why should that be the case? Well, the steady state distribution is exponential. So the steady state distribution has this transform. But because we start in steady state, after an exponential time, you should still be in the stationary distribution. And that is apparently indeed true. So irrespective of the parameter q of that exponential period, you should stay in that exponential distribution. And that is indeed the case. So that was also reassuring. So then we could actually compute the transform of the correlation by doing the standard tricks with transforms. I'm not going to go into the details here. And we eventually find, after lots of calculus, the transform of the correlation in terms of the phi and the psi. So this is exactly what we wanted to have. So in principle, we have all the information that you want to have about the correlation. But of course, it's in the Laplace domain, so what can you do with it? Invert it numerically, maybe. But this is, well, a description of the transform of the correlation. We can ask ourselves again the same question. So can you prove that this correlation is positive, decreasing convex? And you can. So I already announced that I'm going to show that using the concept of complete monotonicity, so I'll do that now. Maybe first a corollary. It's not a very strange corollary. The integral of the autocorrelations is finite. So we are in the case of well, short-range dependence, and that makes sense because the jumps are downward and you cannot jump upward. Okay, a theorem. R is positive, decreasing, and convex. Again, I proved this already for the I mentioned it already for the spectrally positive case, but now I'm going to prove it for the spectrally negative case. And we mimic the proof that we used for the spectrally positive case. So this curly C is the class of completely monotone functions. Think of them as Laplace transforms of positive random variables. Yeah. Okay, So what is the first step? The first step is that we don't look at the transform of R, but we look at the transform of R prime and R double prime. So I wrote them there, the transform of R prime and the transform of R double prime, and by using integration by parts, you can express them in terms of this phi and psi. Remember, we have the transform of R, and we can use that expression to get the transforms of R prime and R double prime. Okay, later on, I promise that I'll come back to that. We will show that this ratio, psi 0 over psi q, is a completely monotone function. So I'm not going to do that now, I'm going to do that later on, but keep it in mind. Okay, what is the next step? Well, the first step is, well, because of this fact, well, we see that row 2 is a completely monotone function because it's just a simple transform of this one, and well, it remains completely monotone. In other words, R double prime should be positive. In other words, R is convex. So that is step 1. Okay, a following thing. Suppose that we know that F is completely monotone, then the G that you define in this way is also completely monotone. Think of the Laplace transform of a residual. There you have this property, right? I mean, it's exactly the same. So this is a standard property of completely monotone functions. It means that minus rho 1 of Q is also completely monotone. In other words, R prime is negative. In other words, R is decreasing. So that is exactly what you wanted to have. And you can do the same step one more time, and then you can prove that rho is actually completely monotone, and you can prove that R is positive because of that. So it's a kind of clean procedure that we already applied in the spectrally positive case, but here in the spectrally negative case you can do exactly the same. Okay, this was part 1. Until now we talked about structural properties of the workload correlation function, and one of the goals of this presentation was also to say something about, well, how to compute numerically by simulation such a correlation. And in order to do so, I first make a small detour. I'm first going to say something about the so-called busy period, because, well, we will see that a busy period is very similar to the workload correlation, and, well, techniques in order to, well, to compute the tail probabilities of this busy period can then be reused to develop techniques for, well, to compute the tail of the workload correlation. So that is the idea. So first we are studying this busy period, and then we're going to use these ideas in for the correlation function. So what is the idea? Well, tau is the first epoch that your Q is empty. So you start off at equilibrium again, and you wait until your Q is empty. P of t is the probability that tau is bigger than t. Well, we again know everything about this tau in terms of transforms. For instance, in the spectrally positive case, well, you can do all kinds of computations. I'm not going to go into details here, but it turns out that the transform of this P of t is known and looks like this. It resembles a little bit the transform of the correlation function. One of the striking things is that also here this psi of theta shows up. A similar thing for the spectrally negative case. Again, I'm not going to go into details, but also in this case you can compute the transform of the probability that tau is bigger than t. And it turns out to be something like this. And also in this case, you see that the formula resembles very much the transform of the workload correlation. I'll say a bit more about that in a minute. One of the things that I proved in passing is this thing. The Laplace transform of tau is given by this formula, and that was the one that I mentioned before. I promised you that I would say something about this thing being completely monotone, and here's the proof. It's indeed the transform of a positive random variable. Well, I mentioned that these formulas very much resemble the formulas for the transforms of the correlation function. And let me be a bit more specific about it. Well, the thing that happens is that the transforms have the same branching point as the transforms of the correlation function. So if you look at the branching points of both expressions, then you will see that they are exactly the same. What do I mean there? Well, suppose you look at a spectrally positive case. Suppose there are light tails. So there is a negative alpha for which you have a solution to this equation. Then it turns out that R and P both decay more or less exponentially, but with the same parameter, namely that branching point. So zeta is the minimizer of phi, and theta star is the phi evaluated in zeta. Well, it's not important to understand this in detail, but the most important thing is, well, they vanish more or less in the same way. So the correlation decay very much looks like the decay of the busy period. And that makes sense, maybe. The same applies to the spectrally negative case. There we also have that both decay more or less exponentially. Q is a negative number, of course. And it's again that branching point. So this gives us the idea that, well, suppose we have an efficient way of simulating the busy period distribution, well, then we can use those ideas to efficiently simulate the workload correlation. Well, the next step is to come up with such an efficient procedure. And how does that work? Well, let's start naively, and then I'll explain why you need such an advanced procedure in the first place. Okay, let's start with that naive way of estimating the tail distribution of tau. Well, a way to do it is to sample tau of I independently in an IID fashion. You count how many of them are bigger than t. You do it n times, you divide by n, and you get a proxy for the probability that you're interested in. Well, you can do that, of course, but it's slow.
So you have to start from stationarity.
Yeah, you start from stationarity. Yeah, you have to be able to start from stationarity in your simulation. That's true. Yeah, there are ways to do that, actually. I can tell a bit more about it after the talk. Sorry?
It takes more time than what is.
Yeah, sometimes there are tricks to do it. There's a paper by Enzor and Peter Glynn, for instance, that has a trick that we could apply here. So that was quite neat. How long does it take? So I already mentioned that it's going to be quite time consuming, and that is indeed the case because, well, suppose that you go on until your width of your confidence interval is a fixed fraction of your estimate. So there is a certain precision that you want to have, let's say epsilon. Well, then you have to go on, so you have to increase your n until this happens. Well, the variance of this S of n looks like this because it's basically a binomial random variable. So there you get more or less p of t over n because p of t is a very small number. Well, then you can compute how big n should be in order to achieve this. And what you will get is that the number of runs that you need is more or less inversely proportional to p of t. So when you make your p of t 10 times smaller, then it takes you 10 times longer to estimate. So that explains why we want to find something more clever. And that something more clever is importance sampling. What is the idea? So we don't sample from the actual distribution, but we sample from a distribution under which the event of interest occurs more frequently. So the idea is to change both, let's say, the Lévy process that applies to the interval 0 to t and the initial distribution at time 0. So we exponentially twist them. I'm not going to go into details about that, but it's a way to change these distributions, and we get some new measure Q of kappa, where kappa is the way to change the distribution at time 0. The question is, How should I do this in order to well, achieve variance reduction? How should I choose these parameters zeta and kappa in order to do that? Well, the idea is that you can compute what under this change of measure is going to be the so-called likelihood. I say that under important sampling, well, the event of interest occurs more frequently, but of course you want to have an unbiased estimator. So you have to compensate for that by weighing all observations by a so-called likelihood. And this likelihood can be computed in this way. Again, I'm not going to go into details. And if you do so, well, then you get a new unbiased estimator. This event occurs more frequently, but you weigh it by small numbers and you get something that is, again, unbiased. Well, I mentioned that you could compute this likelihood L, and I already mentioned that there are two things that you change, namely the distribution of your Lévy process between 0 and t and your initial distribution. For that Lévy process, it kind of makes sense to give it exactly 0 drift, because then, well, busy periods last long, but under all the changes of measure in which this is the case, it's the most likely one. Of course, it's not likely that the queue is going to build up. So that is the idea about, well, using, let's say, a 0 drift for that. The tricky thing is, what should you do with your distribution at time 0? And that's actually a quite technical thing, so I'm not going to say very much about that. In any case, picking kappa as 0, meaning you don't change the measure at time 0 at all, is not a good idea. Because, well, if you look at this formula, well, basically you have to prove that this thing is finite, and I couldn't prove it, and I think I can construct cases in which this is not a case. Meaning that your variance can actually explode. So you have to do something with your distribution at time 0. It turned out that twisting this distribution at time 0 with exactly the same parameter as your Lévy process between 0 and t is the right idea. And then if you do the computations, you will see that you get exactly the right thing. And what you will get is that the number of runs that you need grows sub-exponentially in t. So your probability decays exponentially, but the number of runs that you need in order to have an estimate of given precision grows sub-exponentially. So that is quite nice. And in fact, you can do better. You can even come up with something with bounded relative error, but I'm not going to go into that now. So that is the idea. So we have now the idea of important sampling that we could use for that busy period. The question that we want to solve now, can we use that same idea in order to say something about, well, how to simulate the correlation function? And we can, but it works quite differently, actually. Remember, the thing that we want to estimate is this R of t, which is the correlation of the workload, and that is computed in that way. Remember that in both cases we know this mu. This mu is the steady state workload, and both in the spectrally positive and the spectrally negative case, we knew how to handle that. Also, the variance is something that we know. So the only thing that we don't know is this cross term. So that is the thing that we want to estimate. So one very naive way to estimate the numerator of this thing is by looking at something like this. So you sample n times. You start off at a steady state distribution. You wait until time t. You record these two values, and then you estimate the numerator of that thing in this way. My question to you, we saw that in the case of the busy period, the number of runs that you needed was inversely proportional to the probability that you estimated. What would come out here? What would come out here? Is there somebody with a good intuition? So my question already suggests that it's slightly different. And it is, so I'll show you. What is going on? If you look at, well, the variance of Q0, Qt, and that is, of course, what we need, because that determines, well, the variance of the estimator. Well, then you will see that it goes to a constant. And that is quite different from before, because in the case of the busy period, well, it went to pt over n. And pt over n is something that is small when t grows large, but this doesn't go to 0 when t grows large. It goes to a constant. And it actually means that the number of runs that you need is roughly proportional to 1 over r squared. So that is quite amazing. So it's way worse than in the case of probabilities, because we are estimating correlations. Well, there's another complexity that enters. But we found a clever trick, and the trick is a kind of coupling trick, and that works extremely well. So what did we do? Well, we said, well, this R of t, this correlation, can be written in a different way. This R of t can be written as, well, again, as 1 over v, 1 over the variance, so that is clear. But then you get something like the mean of q0 times qt minus qt star. So I should explain what qt star is. Both q and q star are stationary versions of the workload, but qt star is independent of q0. And you can actually do that. You can actually construct it, namely in the following way. So what do? You sample q0 and q0 star independently of each other. But after that, you use the same driving Lévy process. So how does that look? So you have a q0 and a q0 star, and q0 star maybe behaves like this. And the other process kind of moves in parallel until both busy periods have ended, and then they are coupled. Then they are stuck. They are kind of fixed to each other. So it's a very interesting construction. And you see that it's actually correct. So if you look at this formula, it's another way of representing the correlation.
After the busy period, it becomes 0, yeah?
That is a very good remark. After the busy period, qt and qt star are equal to each other, and it becomes 0. And that already explains that there is such a nice connection between the busy period and the correlation. So it's a very good remark. Qt and Q0 are correlated, but Qt star and Q0 are independent. So that is, well, the benefits. So what is the idea then? Well, we use another simulator for the numerator of our correlation. How do we do it? Well, we just do it in this way, which is basically the sampled version of this mean. So it's nothing more than that. The question is, what do we gain by doing this? Is it any better or not? Well, it is. Fortunately, it is. And how can you see that? Well, the way to do it is the following. So you can split, and then I come back to Sergei's remark, you can split the thing that you want to estimate into 4 terms. All of them represent one of the cases in terms of, well, busy periods that have ended. So in this case, both busy periods are still going on. In this case, the first one is still going on, but the second one has ended. Here, the other way around, and here both have ended. And here you see exactly what Sergei mentioned. If both have ended, then your R minus is actually 0. So there are 3 terms left, and in all of them, at least one of the busy periods still needs to go on. And that explains why you essentially see the busy period asymptotics. So the key observation is that the processes get together more and more. When t grows, in the end, they are together. And for that reason, we have that the variance of the thing that we want to estimate is smaller than, the first step is clear, of course, the second moment, but the second step is because of that property that is written there. And, well, then you can kind of consider all the specific cases, and in each of them, at least one of the busy periods still needs to go on. Well, then there is a kind of technical lemma. I mentioned that at least one of the busy periods still needs to go on, meaning that your tau should be bigger than t, and it turns out that, well, this asymptotic decay rate is smaller than theta star being that decay rate that we already found in the busy period case. So that is in the spectrally positive case. In the spectrally negative case, it's of course q star. And that leads us to this inequality, and in the end we get that this variance divided by r of t looks like this, meaning that the number of runs that you need grows more or less like 1 over r. So we started with something that was 1 over r squared, and we have now something that looks like 1 over r. So it's quite a substantial improvement already. You can make it even better by doing exactly the same trick as what I showed for the busy period. So using important sampling to make busy periods occur more frequently, weigh your observations by likelihood ratios, doing that exactly in the same way as in the busy period case, then you get something that is again sub-exponential, meaning that the number of runs that you need grows sub-exponentially in t. Well, you call such an algorithm logarithmically efficient. Which brings me to the last slide, and the last slide is starts with a kind of general remark. The analysis of the correlation structure of the process after imposing the reflection map, that is actually what I've been doing during this presentation. And the key question was, what can you say about the correlation structure of the workload process? Is that inherited, or does that inherit the correlation structure of the input process? Well, as I argued at the beginning of my talk, it's a very kind of fundamental question. If you think about this question, well, basically two things happen. So you have a correlated input process that is fed into a queue. Well, the queue can be dependent because of the correlation that was present in the input process, but also because of, well, what the reflection map does. So in that Lévy case, well, the input process didn't have any correlation, so it's really the effect of the correlation map. In the FBM case, well, the busy period is actually white Boolean. So there, and we conjecture, the busy periods asymptotics are white Boolean, and in that case, we conjecture that the correlation of the workload process very much looks like the correlation structure of the input process. So there, the opposite effect apparently dominates. And yeah, it would be nice to get some understanding about, well, how these two effects, well, work. So I also mentioned that it's hard to solve questions of this type for the Gaussian case, so for fractional Brownian motion, for instance. But for this Lévy case, I showed that, well, you can come up with a very explicit analysis. You can find structural results. You can find transforms, tail asymptotics, and efficient simulation. And that was it.
Just a question you asked. That was only about fractional Brownian motion. That is, you know the answers in other cases.
It's a very good question. I mentioned FBM because it's probably the most appealing case, but in fact we didn't solve that question for any other process. So probably these results for the Lévy case are among the only results about the correlation function. Even for the case of on-off sources, I don't know how the workload correlation decays. So there is the feeling that it looks very much like the MG1 case, but I wouldn't know how to solve that. The most important thing for that on-off case is that we don't have the transform of, well, the workloads after an exponential amount of time, and that is apparently the thing that you need. Other questions? Takis?
Couple of questions. First question is, just to understand, you said that in the spectrally positive case, you base your computation on the result of Kellen-Boxma 2006.
Yeah, but it's actually older, I think. But you probably knew that. But it's also in the Asmussen book. And,
Okay.
yeah.
And the second one is this formula of Pistorius.
Yeah.
Once you have that, then you can get the structure of the Laplace function.
Yeah, exactly. Yeah.
Function. And then do the Tauberian theorem to get out of T? I mean,
Tauberian theorem to get what?
to get the behavior of R of T as T goes to infinity.
I guess you could use that, but I didn't do that here. But I guess you could do that. So it could actually be interesting to see what happens. So the only remark I made now is that there is a branching point, and that is probably the thing that matters. But yeah, how that works, I don't know.
Then, questions. Yeah, about this the busy period, you simulate you're in steady state.
Yeah.
You look at the first time
Yeah.
the thing empties.
Yeah.
What if you look the whole excursion from zero? I mean, the two distributions, can you relate them?
The whole. Oh, okay, because there's quite a bit of independence.
Starting from zero. Start from zero.
Starting from zero.
Start from zero.
Uh,
And then wait until the time first time to get back
that's,
to zero.
that would
That's a
save a
nice-
lot of effort.
nice distribution.
Yeah, that's a good question because it would save a lot of effort at time zero, and that would actually be quite interesting if that were possible.
If the two distributions are related, in the suspect they are.
Yeah.
At least in terms of asymptotics, one has lighter tail.
Yeah, so the asymptotics are the same up to a constant, I think.
The two busy periods?
But you run into problems with, let's say, the Brownian case, because, well,
Well, the Brownian case, right. But yeah, let's think of a case where the input is
MG1 type.
is singular with respect to the back
Yeah,
measure like
yeah,
that. So you
yeah.
get-
Yeah, then you could actually try this. So it's,
So you consider the busy cycle, yeah?
Huh?
On the, you s-
yeah. But it could actually be possible because of the independence that you have. By the way, that independence also is also the reason why this coupling trick works. So you cannot do the same coupling trick for instance, FBM, because, well, the full memory plays a role when you want to say something about the future. So that is something very powerful. David?
Is the correlation structure of the workload process the same as the correlation structure of the departure process?
Yeah, that's a very good question. I remember us discussing that 2 years ago, and I still don't know. There should be quite a strong relation there, but I don't dare to say something about that. Of course, there is, well, Hurstiness that couples everything but it's under a specific scaling, I would say, and it's a slightly different concept. But of course, there are relations between Hurstiness and this kind of stuff. Yeah. Well, let's thank the speaker.